You've just wired a brand new remote slave device, like a Digiforce 9310, into your master PLC using PROFIBUS or Profinet. The physical connection is solid. Millions of bits fire back and forth through the industrial cable every second, and your run lights are solid green. The physical bus is healthy, and the nodes are communicating exactly as scheduled, but the resulting data is useless. You were expecting a simple analog target value of 1234.56. Instead, your PLC tag is populated with a massive, impossible number, over 23 quintillion. This happens because standardized configuration files do an excellent job of constructing the communication pipeline between devices, but they do not translate the payload traveling inside it. Solving these discrepancies requires moving past the automation of the engineering tool to manually verify the network's byte-level architecture. The first step in integrating a field bus device is usually importing its general station description, or GSD file. This electronic datasheet gives the master controller the physical properties of the slave device. It defines the supported baud rates, the specific bit times, and exactly how many cyclic bytes will be sent and received during each loop. This configuration window shows connection parameters applied to a module. Loading GSD data populates settings, like target station numbers and timer intervals. While these fields establish the pipeline's size and timing, the file contains no definitions for the actual data types inside the payload. The master PLC knows exactly how many bytes of data to expect from the remote station, but it has zero context for what those bytes mean, or how they should be interpreted. If you treat a GSD file as a complete, start-to-finish integration tool, you risk the systematic misinterpretation of complex analog data. The first trap when cross-vendor devices share memory blocks is the misalignment of register indexes. In Modbus, data representation operates on a binary level, so the mathematical counting must always begin at address 0, but manufacturers design for human readability. To an operator, the first value is simply number 1, so they shift the index to start there. This Solvimus document highlights how this shift causes failures. It warns that if a remote station starts counting at 1, reading registers 24 and 25 for a 32-bit float actually returns registers 23 and 24. You've split the data in half. If the master and the slave disagree on the starting line, the PLC will read corrupted, shifted memory blocks. Problems still occur even when the register addresses align perfectly and the analog data remains unreadable. Most industrial control systems rely on the IEEE 754 standard as the architecture for processing 32-bit floating point numbers. To transmit a 32-bit float over a network, it must be broken down into 4 distinct 8-bit bytes. The receiving PLC must read those bytes in a specific sequence, known as endianness. When a slave device packages a floating point number for transfer, it transmits the sign byte first, followed by the rest. However, master systems expect to receive that sign byte in the highest of the 4 addresses, not the lowest. When you drop the slave's linear transmission into the master's reversed memory expectation, you scramble the math. The decimal point moves, the sign flips, and the target value becomes 23 quintillion. Because the bytes are physically arriving on time and in the correct size, the network does not see a problem. Hardware-level endianness conflicts will destroy data integrity without ever triggering a network fault. Resolving this requires a manual engineering intervention, reversing the payload sequence before the PLC interprets it. You execute this using a byte swap or word swap instruction directly within your PLC's ladder logic or structured text. By reordering the bytes to match the master's native architecture, the math resolves and the target value is restored. When commissioning a new device, validate the integration in 3 steps. First, import the GSD file and validate the physical layer connection. Second, check the manufacturer's documentation to verify whether the remote station is using a 0-based logical index or a 1-based human register offset. Third, align the hardware endianness by programming necessary byte swaps for any complex analog data types. Reconciling these unseen data translations is exactly what allows diverse, cross-vendor machines across the factory floor to operate in perfect unison. Field bus reliability across a multi-vendor system is achieved when an engineer validates the underlying byte-level architecture, rather than relying on the configuration file alone.
Thanks for watching. Please visit the channel for more content. Don't forget to subscribe, like if helpful, and comment if something is wrong.